The centripetal force is a force that always gives people a lot of problems, so we'll discuss it a bit here, but we'll definitely have to work on some of the more finer details when we meet in the classroom. Here's where the centripetal force comes from. It has to do with objects that are traveling in circles. So it could be going around a circular track, around a roller coaster, whatever the case may be, it's things traveling in circles. Here's the way it sort of works. Suppose you're trying to travel in a circle then, and this is the track you're trying to maintain. Looks something like that. There's the track you're trying to maintain. And say at this point right here, your velocity is carrying you straight up this way. There's your velocity vector. Now, if you want to stay on this circle, a moment later in time, your velocity vector better change, a better point along that circle. And if you want to maintain yourself on the circle, you have to keep changing your velocity to keep yourself on the circle. So there's V there, there's V there, there's V there. Your velocity vector has to keep changing like this so you can keep going around the circle. Remember that the velocity vector sort of dictates the position you're going to be in next, so you have to keep yourself on the circle. So the question now is, well, what can you do, or how could you possibly get your velocity vector to keep pointing around the circle like that? And the way you would do that then is you would get on a circle like this, and something would have to pull you inwards towards the center of the circle, say some force F like that. Now, how do I know it would be a force F like that? Well, it's for the following reason. We know that acceleration is F over m. So if we take the mass of the object that's going around the circle, and we take the force that's acting on it, if we divide the two, we'll get the acceleration. Why am I so interested in acceleration? Because it's accelerations that change velocities, because we know that v is equal to v naught plus a times delta t. So what is actually occurring between these two positions, say here and here, is a little bit of time is going by. That's just traveling around the circle here. And the only way I can change the velocity is by applying an acceleration onto an object. So I am concerned with what this acceleration would be. So it turns out then that an acceleration that always points inwards toward the center of the circle and has a particular magnitude, which I'll tell you about in just a second, is what you would need then to maintain yourself throughout the circle here. So over here, the force would be inwards. Over here, the force would be inwards. Over here, the force would be inwards. All these inwards forces like that, all these F's around there like that, would maintain you in the circle. The V's here, if you look very carefully, the V's are tangential to the circle. And the F's here are always radial, or radially inwards. Something like that. So the V's are tangential, the F's are radially inwards, and by these definitions here, if the force is radial and the V is tangential, all of these angles here have to be 90-degree angles like that, like that. They're all 90-degree angles, as they must be to go around the circle like that. Now, you can have any old force like that, and you may or may not maintain yourself on a circle, but if the magnitude of your force here, say if the magnitude here is equal to the mass of your object times the velocity you're trying to travel squared, divided by the radius of the circle that you're trying to maintain. If you're trying to maintain yourself on a circular radius r, if you have this magnitude of the force then the force that you're applying here is called the centripetal force. If you look up centripetal in the dictionary, it means seeking the center. That's exactly what the forces do. They always point towards the center. So if you can get yourself a magnitude of mv squared over r, you will maintain yourself in a circle, and that's the nature of the centripetal force. Now, the confusion comes from the following, and we'll have to embellish this a bit more in the lecture, maybe with some demonstrations and so on. That suppose you were riding in a car here that was maintaining a circle like this. You don't feel yourself being pulled in towards the center of the circle. In fact, you feel just the opposite. You actually feel yourself being pushed out that way, say towards the right window. Now you have to just stop for a minute and imagine this. Imagine you're in a car and you're going straight and suddenly the driver turns towards the left to make this circle here. You are going to feel yourself being thrown out towards the right. That force is a strange inertial force that has to come with the fact that has to do with the fact that it is actually the car which is in the circle. You're just a passenger in the car sitting on the seat. It has to do with friction between you and the seat and your own inertia and things like that. But in a nutshell, it's the car which is trying to move through the circle like this, but your velocity is going to cause you to go straight again owing to your own inertia and some things like that. Again, it's sort of a confusing point that we'll have to talk about, but what you feel is an outwards going force. So what I'm just going to declare then is that the centripetal force is the only real force, but this other one, this outwards one here, is called the centrifugal force. Centrifugal force. That's the outwards one here. And I just want to put that it is a fake force. It doesn't actually exist. It's a perception you feel because, again, it's the car which is in the circle and you're just a passenger in a car. It's a two-object problem here. The car turns to the left, But your inertia wants to carry you straight, so you see the right door of the car sort of approaching you as you continue in your straight path, but your perception is that something is pulling you out towards the right, even though the car is going towards the left. Very confusing. You might have to pause and rewind and read your book and listen to that statement several times. We'll talk about it more in the lecture. But the bottom line is, whenever you're working a centrifugal force problem, or a problem that involves something going in a circle, the actual force that you would write on it then would be mv squared over r, and you would draw it outwards like that, and that will sort of allow you to get the problem solved, although the perception of what's actually going on is very confusing, and you sort of have to dig deep and think about it a bit before you can fully understand it. But in terms of just getting yourself through some of the problems and getting some concepts to work out, it'll be fine to say mv squared over r outwards and label it as centrifugal force.